Chapter 15 in our textbook is entitled Chemical Equilibrium. Now, in previous chapters, we've talked about the concept of dynamic equilibrium. This is a condition under which we see two opposing processes taking place at the same rate. For example, the freezing of a sample of matter and the melting of a sample of matter. When the rates of those two opposing processes is the same, then the situation, the condition is known as dynamic equilibrium. Well, that refers to any particular set of processes, whether they be physical or chemical in nature. Chemical equilibrium occurs when a reaction and its reverse reaction proceed at the same rate. Let's take into consideration nitrogen dioxide. Nitrogen dioxide is a brown gas. Dinitrogen tetroxide is a colorless gas. When a sample of dinitrogen monoxide at room temperature decomposes, it will decompose in order to form nitrogen dioxide. So a colorless gas will become a brown gas. And the way that we know that the reaction has gone as far as it's going to go is essentially when the reaction no longer gets any browner. The interesting thing to take note of, if I were to take a sample of nitrogen dioxide gas and leave it to its own devices, then it would actually get lighter. Why? Because nitrogen dioxide will also react with itself in order to form dinitrogen tetroxide. So both reactions are constantly occurring at the same time. If you have a sample of nitrogen dioxide, it is going to combine with itself in order to form dinitrogen tetroxide. If you have a sample of dinitrogen tetroxide, then it is going to decompose in order to form nitrogen dioxide. The point at which we no longer see a color change suggests that we have reached the end point of this reaction. Now, two important things to take note of about a system as it approaches equilibrium. First of all, both the forward and reverse reactions are occurring, and they are doing so at the same rate. If you look at the image on the right, you will see that the rate of both of these processes ultimately ends up being the same over time. When equilibrium is achieved, then the rates of these two reactions are equal. At the same time, the concentrations of our components are changing as long as these reactions are occurring. If we have nitrogen dioxide, we're going to consume nitrogen dioxide until we form a certain amount of dinitrogen tetroxide. If we are consuming dinitrogen tetroxide, we're going to see the decomposition of it until we form so much nitrogen dioxide. As these two reactions reach equilibrium, we ultimately come to a point where the concentrations of our components are no longer changing. In the previous slide, we saw that the colorless dinitrogen tetroxide would get browner. The brown nitrogen dioxide would get less brown. Well, what's the stopping point? The stopping point is equilibrium. So if a chemical system is in dynamic equilibrium, if we have indeed established chemical equilibrium, then products are constantly being made, but at the same time, reactants are being made and at the same rate. So the forward reaction is proceeding at the same rate as the reverse reaction. If that's the case, then the total amount of reactant and product isn't going to change. It's going to remain constant. For every amount of reactant that is consumed and forming product, we're going to see product being consumed and forming reactant. Neither reactant nor product can escape the system. But most importantly, at least from a calculation point of view, there is a ratio of concentration terms that is constant. If we know that the amount of reactant and the amount of product remain unchanged overall at equilibrium, there has to be some relationship between the concentration of our products and the concentration of our reactants. It doesn't matter if we start out with nothing but reactant and we see the formation of product, or if we start off with nothing but product and see the formation of reactant. It doesn't even matter if we put some reactant and some product into a reaction vessel. They're going to react in such a fashion that they walk away at equilibrium. And at equilibrium, there is a ratio of concentrations that must be true. Now, when we write the chemical equation for a reaction that is considered an equilibrium reaction, since the reaction goes both in the forward direction and the reverse direction, we write the chemical equation, but instead of a single-sided arrow going from left to right, going from reactants to products, we see a double-sided arrow. Equilibrium is indicated with this double-sided arrow, suggesting that the reactions are taking place in both directions. Let's take into consideration the Haber process, named after German chemist Fritz Haber, who developed it. This process involves the industrial preparation of ammonia from elemental nitrogen and hydrogen. Since ammonia is a good source of fixed nitrogen for plants, much of the ammonia that is produced industrially is used as a fertilizer. In order for this reaction to proceed efficiently, it is often carried out at high temperature and pressure. So if we take nitrogen and hydrogen at high temperature and pressure, we will see the production of ammonia. At the same time, at high temperatures and pressures, ammonia will decompose in order to form nitrogen gas and hydrogen gas. So if we start with a mixture of nitrogen and hydrogen in any proportions, the reaction is going to proceed towards equilibrium, and we're going to end up with a constant concentration of nitrogen, hydrogen, and ammonia. If we start with simply ammonia and no nitrogen or hydrogen, then we will see the reverse reaction proceed, and we will still see a constant concentration of nitrogen, hydrogen, and ammonia after equilibrium is reached, no matter what the starting composition of the reactants and products is. The equilibrium mixture is going to contain the same relative concentrations of products and reactants. Now, this ratio is related through what we call the equilibrium constant. It is represented by a capital K, a capital K sub C. So the equilibrium constant, not to be confused with the rate constant, which is a lowercase k, is going to be equal to the ratio of our products to our reactants, stoichiometrically weighed as coefficients. So if you look at the bottom of this slide, you will see the formula for the equilibrium constant involves ammonia, since it is a product, the concentration of ammonia raised to the second power, because if you note the stoichiometry of the reaction, 2 moles of ammonia are formed as a result of 1 mole of nitrogen and 3 moles of hydrogen combining. In the denominator of this ratio, we see nitrogen and hydrogen raised to their stoichiometric coefficients, since nitrogen is only present in 1 molar amounts and hydrogen in 3 molar amounts. Then we would see our hydrogen cubed or raised to the third power. So regardless of how we start, whether it's with all reactant, whether it's with all product, whether we have a mixture of nitrogen and hydrogen and ammonia thrown into a reaction vessel, at the end of the day, when equilibrium is reached, there will be a value. a constant ratio of products to reactants that will obey this very expression. That idea is reflected in these two images. If the green line represents the concentration of hydrogen, the blue line represents the concentration of nitrogen, and the red line represents the concentration of ammonia. If we start with no ammonia, but we have some nitrogen and some hydrogen, we're going to see that they are going to be consumed over time. We see that their concentration decreases while the concentration of ammonia increases. And they are going to do so until they reach equilibrium, at which point the concentration of all three is going to remain the same. Similarly, if we start out with nothing but ammonia, as is indicated in the right-hand image, and no nitrogen and no hydrogen, we're going to see nitrogen formed. We're going to see hydrogen formed as a result of ammonia decomposing. And those concentrations are going to change up until equilibrium is reached. Now let's take a look at that relationship, the relationship that we called the equilibrium constant. The equilibrium constant can be expressed by looking at the following reaction. If we have A moles of A reacting with B moles of B, giving us D moles of D and E moles of E, then in general, the equilibrium expression for this particular reaction, once again, involves products raised to their stoichiometric coefficients divided by reactants. The concentration of each product raised to its stoichiometric coefficient multiplied by one another, divided by the concentration of the reactants stoichiometrically raised to those coefficients. Now, since pressure is directly proportional to concentration for gases, then the equilibrium constant expression can also, for a gas phase system, involve those pressures instead of the concentrations. And sometimes it's easier to measure gas pressures than it is gas concentrations. How are pressure and concentration related? Well, I'm glad you asked. If the gases are behaving ideally, then PV is equal to nRT. If we rearrange this in such a fashion where we get P is equal to N divided by V times RT, the relationship between N and V, moles per liter, that sounds like a measure of concentration. Specifically, it sounds like molarity. So the relationship between pressure and concentration is indeed a direct proportionality. So the result, if we were to, instead of looking at the equilibrium constant with respect to concentration, or K sub C, the result would be K sub P, the equilibrium constant with respect to pressure. So we would rearrange our PV equals nRT, establishing a new equilibrium constant expression, relating both the equilibrium constant with respect to pressure to that of concentration. Now let's revisit our original equilibrium reaction system that involved dinitrogen tetroxide and nitrogen dioxide. A series of experiments were performed in which we dealt with initial concentrations of NO2 and N2O4 in varying amounts. Now, again, these four experiments were performed with varying initial concentrations of N2O4 and NO2. Under each set of conditions, the reactions were allowed to reach equilibrium. And in these four instances, we see different equilibrium concentrations of N2O4 and NO2 achieved. But at the end of the day, When we take the ratio of products to reactants stoichiometrically weighed, regardless of the absolute amount of product that's formed, regardless of the absolute amount of reactant that is formed, we see that K sub C value ultimately is the same across the board. Now, something can be said about the absolute value of K. Since K represents the ratio of products to reactants, products over reactants, if K is a very large number, if K is much greater than 1, then the ratio of products to reactants is high, which means that products are going to be prevalent at equilibrium. Our equilibrium mixture will have a lot of products compared to the amount of reactants. Conversely, if K is very, very small, if K is significantly less than 1, then the reaction prefers that reactants be formed. Reactants are going to dominate the equilibrium mixture. And it is said that equilibrium essentially lies to the left. Now, it's important to note that the value of K is dependent upon the way in which we write our equilibrium reaction. If we write the reaction for the decomposition of dinitrogen tetroxide into 2 moles of nitrogen dioxide, then nitrogen dioxide is the product, while dinitrogen tetroxide is the reactant. So looking at that ratio, for the data that we saw previously at 100 degrees Celsius would give us a value of 0.212. If we write the reaction in reverse, if we consider the reaction of nitrogen dioxide combining in order to form dinitrogen tetroxide, the roles of reactant and product have reversed. So nitrogen dioxide is now our reactant. Dinitrogen tetroxide is our product. They will switch places. In other words, the K sub C value for this reaction would be the reciprocal of the K sub C value for the forward reaction, or for the opposite. Once again, we have to be very careful how we write our reaction. If we write our reaction with different stoichiometries, then the K sub C value will reflect that as well. Both of these reactions speak to the formation of nitrogen dioxide from dinitrogen tetroxide. But simply by multiplying the first equation by 2 across the board, we haven't affected the actual stoichiometry. There's still the same amount of nitrogen on one side of the equation and oxygen on one side of the equation as we see on the other. But the stoichiometry changing suggests that our K sub C value will change as well. In this instance, since the stoichiometry is essentially doubled, then the equilibrium constant will be squared. Now, if we have 2 reactions that consecutively achieve equilibrium, then their equations can be added together in order to give a single equilibrium. For example, let's look at the system that involves nitrosyl bromide decomposing in order to form nitrogen monoxide and bromine gas. That equilibrium system has a K value of 0.014. Bromine can then react with chlorine gas in order to form BrCl, which results in an equilibrium and an equilibrium constant value of 7.2. If we sum up those 2 reactions in which essentially bromine can be considered as an intermediate, then we see nitrosyl bromide reacting with chlorine in order to form nitrogen monoxide and BrCl as a product. This equilibrium system has an equilibrium constant that would be the product of the prior two equilibrium constants. And that's mathematically taking into consideration the products and reactants of each reaction and relating them accordingly to the overall reaction. Now, the concept of equilibrium can exist in a single phase system or a system between multiple phases or states of matter. The difference lies in what we call or categorize as homogeneous equilibria as opposed to heterogeneous equilibria. Homogeneous equilibria occur when all of the reactants and the products are in the same phase. This would be the case with the systems that we have seen before. With the Haber process, we see elemental nitrogen in the gas phase reacting with elemental hydrogen in the gas phase in order to form ammonia in the gas phase. All of those components in the gas phase, in the same phase, suggest homogeneous equilibria. Heterogeneous equilibria occur when all of the reactants and the products are not in the same phase. And we will explore that in just a moment. Now, it should be noted that since the equilibrium constant expression is based on the concentration of products over reactants, the concentration of a solid does not change. If we talk about concentration in terms of moles per liter, if I have a sample of solid gold, if I have so many moles of gold and it takes up so much space, if I cut that ratio in half, or rather, excuse me, if I cut the amount of gold in half, it is going to take up half as much space. So the ratio of moles per liter is going to remain the same. The concentration of a pure solid will not change. Similarly, the concentration of a pure liquid will not change. So it is for this reason that pure solids and liquids are omitted from the equilibrium constant expression. Where those values would be inserted, we simply replace them with the number 1. And on the next slide, we will see not only an example of this, but also of heterogeneous equilibria. Here we see a system that involves the decomposition of calcium carbonate into calcium oxide and carbon dioxide. Now, since calcium carbonate is a solid, since calcium oxide is a solid, we do not represent them in the equilibrium constant expression. Whereas we would typically think products over reactants, we would typically think that calcium oxide and carbon dioxide would be our products on top of the ratio, and calcium carbonate would be underneath as the denominator. But since calcium carbonate and calcium oxide both exist in the solid phase, their concentrations will remain unchanged. The amount of substance in terms of moles may change, but the concentration moles per liter remains unchanged. So we would reflect that by placing a 1 in place of each of their spaces in the equilibrium constant expression, which simply suggests that the equilibrium constant with respect to concentration is equal to the concentration of carbon dioxide. And if we were to relate that to the equilibrium constant with respect to pressure, then it would be the pressure exerted by carbon dioxide in the system. Now, that is all that we're going to talk about for the time being. Next lecture, we're going to actually calculate some values with respect to equilibrium. How do we know when a system has reached equilibrium? If I have a reaction mixture, how can I tell if that reaction mixture is at equilibrium? And if it isn't, Can I predict in which direction a reaction will proceed in order to reach equilibrium? The answer to all of those questions and more coming up on your next lecture. Thank you for your time. Have a great day and stay safe.